Okay, welcome you all to my video lecture presentation. Myself C. Ashok Kumar, Professor, Department of EEE, MLR IT. And my course name is Electronic Device and Circuits. And today's topic name is PN Junction Diode Part 1. And the overview of my presentation will go on like this. First, I will be saying about how the PN junction diode is formed. And then I will be discussing about the transport phenomena of charge carriers inside the PN junction diode. Two types of currents will be existed by the transport phenomena. One is called as a diffusion current, second one is called as a drift current. And also next I will be discussing about what are the different operating conditions of the diode. So out of which I will be taking the first type of operating condition, that is called as a zero bias operation. And finally, I will be recapping all the things whatever I discussed in this lecture. And the textbooks referred are, the first one is Jacob Millman. The title of the book is Electronic Device and Circuits, McGraw-Hill Education. And next book is Robert Ballstead and Neshelsky, Electronic Device and Circuit Theory, Pearson Publishers. And the third book is Sally Vahanan and N. Suresh Kumar, and the title is Electronic Device and Circuits, McGraw-Hill Education. And whatever the slides, images I have taken from by referring all these textbooks, right? Okay, first topic, PN junction as a diode. In the last discussion, we discussed about the extrinsic semiconductors. Two types are there basically. One is called as N-type, second one is called as P-type. So in the N-type, we doped the pentavalent atom into the silicon system, by which a extra free electron will be there in the conduction band. And if you take a P-type, when you are doping the impurity atom, trivalent atom into the silicon crystal, by each impurity atom doping, we are able to have one hole in the valence band. So two types of extrinsic semiconductors are there. One is called as N-type, second one is called as P-type. So whenever if you take any silicon material, let it be silicon or a germanium material. So whenever you dope one end of silicon with P-type material and other end with the N-type material, as you can see here, a PN junction diode is formed like this. As you can see here, this part I am doping with P-type material and this part I am doping with N-type material. Together, as you can see here, a PN junction diode is formed. And here, as you can see here, this particular region is called as a junction. Junction is separating both the P region and N region. Okay. So if you want to represent this P-type semiconductor and N-type semiconductor, a schematic representation is there. Suppose here I am taking N-type. Okay. So N-type can be represented like this. As I already said, N-type means we are doping a pentavalent atom, impurity atom into the system. So thereby it is donating one free electron for the system. So that's why here it is becoming a positive ion covered with free electron. So this can be represented like this. A positive ion covered with free electron. A positive ion covered with free electron. Positive ion covered with free electron. So here I am representing like this. This is an N-type material I am representing like this. Okay. So it is a donor ion which is a positive ion covered with free electron. So this is about N-type material. And what about P-type material? P-type material means whenever you are doping impurity atom into the system, it wants to accept an electron from the nearest covalent bond. That's why it will be becoming acceptor ion. That means it is represented as a negative ion covered with hole. Hole carries positive charge. Okay. So here I am representing the P-type material like this. Acceptor ion covered with hole. So that's why here the schematic representation will be like this. Okay. So this is P region and this is N region. Okay. So this is about the representation of PN junction diode. This is the P region and this is N region. N region is represented by taking a donor ion, positive ion covered with free electron, and also as you can see here, along with free electrons, the holes also will be there in the N-type material. That's why here in a minority manner here I am going for some holes like this. Similarly, in the P-type, the minority carriers are electrons. So that's why here I am going for some holes in a minority level. So majority carriers in the P-type are holes and majority carriers in the N-type are electrons. Okay. So next is about the transport phenomena that happens inside the PN junction diode. So the transport phenomena of the charge carriers in the PN junction diode will be by two mechanisms. One is called as a diffusion mechanism and second one is called as a drift mechanism. So when the diffusion mechanism comes into the picture and when the drift mechanism comes into the picture means inside the device, let us discuss here. So the diffusion phenomena will be in the PN junction diode without applying any external biasing voltage. It will be occurring inside the device when there is a concentration gradient. What do you mean by concentration gradient? Means, as you can see here, this is the region of electrons here, the total region. As you can see, if you observe this particular region, the concentration of electrons are more, and if you observe here, the concentration of electrons is less. So there is a concentration gradient, variation in the concentration. If you observe at different places, if you observe here, the concentration of electrons is more, and if you observe the concentration of holes here, it is less. Okay. So due to this, the diffusion phenomena comes into the picture. That means the electrons which are at higher concentration will be moving to the place where they are in the lower concentration. That means the electrons will be moving from this area to this area, higher concentration to lower concentration. This is called as the diffusion mechanism, by which the movement of electron is happening here, by which the current will be produced. That current is called as a diffusion current. Okay. So the diffusion current happens inside the PN junction diode without applying the external biasing voltage. Okay. That is due to the diffusion mechanism. And if you write by equation, so this can be written like this: Jn, that is the current density due to the movement of holes due to the diffusion mechanism. That this can be written like this: Jn is equal to Q into dn by dx. So dn by dx is, as you can see here, n stands for the electronic concentration. Okay. And here x means the distance from the junction towards right side or towards the left side. Okay. Distance along the device from the junction, that is x. Okay. As you can see here, the concentration of electrons will be decreased if you move away from the junction. Okay. So that's why here it is represented as dn by dx. So Jn is directly proportional to dn by dx, concentration gradient. As you can see here, Q is the charge of the electron and dn is the diffusion constant and dn by dx is the concentration gradient. This is the equation. Current density due to electron movement in a semiconductor device due to the diffusion mechanism is, this is the equation. Jn is equal to current density is equal to Q into dn by dx. So this is about the diffusion mechanism. Next, let us discuss about the drift mechanism. And the drift mechanism comes into the picture only when you are applying an electric field to the diode. Okay. So that's why, as you can see here, we are applying a external biasing voltage, and these are all electrons here. So these electrons are getting attracted towards the positive terminal of the battery. Okay. The electrons, you know, they carries negative charge and they are getting attracted towards the positive terminal of the battery, and thereby the movement of electron is happening here, which produces a current. that current is called as a drift current. So whenever you are applying an electric field, what happens here is it exerts a force on the electrons by increasing its velocity, that is called as a drift velocity, and the mobility will be increased, which in turn increases the current. Okay, this is about the drift mechanism by which the drift current comes into the picture. So for drift current also, here I am writing one more equation. This Jn indicates the current density due to the electron. Jp means the current density due to holes. Here I am, as an example, I am writing only the current density due to the movement of electrons only. Okay. Similarly, here the current density due to the movement of electrons by the drift mechanism equation can be written as like this: Jn is equal to n into q into mu n into E. So n is the electron concentration and q is the charge of the electron, and mu n, as you know, mu n is the mobility of the electron, and E, capital E, is the applied electric field. So that's why here the equation goes on like this: Jn is equal to n into q into mu n into E. So mu n is the mobility. Whenever you are applying the electric field, what happens here is the mobility of the electron will be increased. So these are the equations that define both the diffusion mechanism and drift mechanism. So total current inside the PN junction diode is due to the combination of drift current as well as diffusion current. So total current I can be written as current due to diffusion plus current due to drift. So next, about the diode operating conditions. So as you can see here, three different operating conditions are there for the diode, PN junction diode. One is called as a no bias, second one is called as a forward bias, and third one is called as a reverse bias. In this lecture, I will be concentrating only on no bias. In the next coming lecture, I will be saying about forward bias and reverse bias. Okay. So this, as you can see here, first one is a zero bias. Zero bias, as you can see here, this is a PN junction diode, and as you can see, this P side, the terminal is called as a anode, and the N side, the terminal, it is called as a cathode. Anode and cathode. The terminals of PN junction diode are anode and cathode. Anode is connected to P side, and cathode is connected to N side. Okay. So zero bias, that means here I am not connecting any external electric field, and external biasing voltage I am not providing. That's why I am calling it as a zero bias. So next operating mode is the forward bias. As you can see here, P is connected to positive terminal of the battery and N is connected to negative terminal of the battery. So that's why this particular mode of operation, it is called as a forward bias. Next, third one, reverse bias. So as you can see here, the P, that means anode, is connected to negative terminal of the battery and cathode is connected to positive terminal of the battery, just in a reverse manner. Okay. So these are the three different operating conditions. One by one I will be explaining. First I am taking the zero bias. So before taking the zero bias, let us have a glance upon this PN junction diode, how to represent. As you can see here, this is a PN junction diode. How the P is represented and N is represented. N is represented as a donor ion, positive ion covered with free electron, and P side, a acceptor ion, negative ion covered with hole. So at zero bias, I am not going to apply any external biasing voltage. So as you can see, the concentration of holes at the P side is more when compared with N side. Okay. And the concentration of electrons are more in the N side when you compare with the P side. Okay. So concentration variation is there, concentration gradient is there. Suppose if you take about the hole concentration, as you know, in the P side, the majority carriers are holes. So holes are more here, and in the N side, the majority carriers are electrons. Okay. That's why here there is a variation in the concentration of holes when you check at P side, when you check at N side. So that's why what happens here, the diffusion mechanism comes into the picture, and the holes has to move from P side to N side in this manner. okay, by the diffusion mechanism. Why? Because a concentration gradient is happening here. Similarly, if you observe n region, the majority carriers are electrons. Electrons are more here when you compare with p region. So that's why here electrons will move from higher concentration to lower concentration, from n side to p side. So this is the direction of the movement of electrons, and this is the direction of holes movement from p side to n side, and electron movement is from n side to p side. Okay, that is due to the diffusion mechanism. And mostly affected region of this PN junction diode is the junction. Okay, so as you can see here a hole is there, and here a free electron is there. At the junction, due to the mechanism of diffusion, in the process of diffusion, what happens here? This hole will be combined with this free electron. Similarly, this hole will be combined with this free electron. Both will be combined and they will be disappeared. They will be disappeared. Okay, both will be combined and they will be disappeared. So earlier these ions are covered. As you can see here, this negative ion is covered with hole here, and this positive ion is covered with electron. So whenever both the hole as well as free electrons are combined, they will be disappearing. Whenever the disappearance happens, these two ions are uncovered. Similarly here, if you take this ion and this ion, as you can see, this hole will be combined with this free electron, and here this negative ion is uncovered and this positive ion is uncovered. Okay, so let us observe the diagram about this explanation. As you can see here, so here, as you can see here, particularly at the junction, what is happened here? Due to the diffusion mechanism, earlier the ions are covered with either hole or free electron. Now they are uncovered due to the recombination of hole with free electron. So now what happened here? A depletion region is created here. A depletion region is created here. Depletion region means it is depleted of charge carriers. Depleted of charge carrier means earlier they are covered with charge carriers. Now no coverage is there. So this particular region does not contain any free carriers, either electron or hole. So that's why this particular region is called as a depletion region. As you can see here, this particular region, it is a combination of a positive charge, and this is the combination of a negative charge. They are immobile ions. They don't contribute anything for the conduction of the device. They are immobile. So that's why this region, it is called as a depletion region. So whenever this depletion region is formed inside the device, there won't be any further movement of holes from p side to n side, and there won't be any further movement of electrons from n side to p side. Why? Because whenever hole is moved from here to here, as you can see here, a positive charge is there. Due to repulsion, it won't reach into the n side. Similarly, whenever electron is moved from n side to p side, as you can see here, a negative charge is there. Due to repulsion, it can't move further, so it stops here only. So whenever the depletion region is created inside the device, there won't be any further movement of holes from p side to n side and electrons from n side to p side. So the representation schematic symbol will be like this: diode symbol. VD, we are not applying any voltage, so that's why the current also is 0 milliamperes. Okay, no external voltage is applied. V is equal to 0 and I is equal to 0, and only a modest depletion region exists. So by this creation of this depletion region, what happens? Let us see here. So this is a diagram. Earlier I explained. As you can see, at the center a depletion region is created. This is a junction. Okay, this is a positive charge, this is a negative charge. So here three different diagrams are represented. So before checking the diagrams, let me write some equations related with this diagram. First one is the Poisson equation, that can be written like this: d square v by dx square is equal to minus rho by e. So this rho is the charge density. This, as you can see, charge is there, positive charge, negative charge, and E is the permittivity, and V is the voltage, and X is the distance here. Distance from the junction. This is a junction, x is equal to 0, this is x and this is x. Okay. So by Poisson equation can be written like this. So this particular graph, this is x here. Okay. So charge versus the distance from junction along the diode. Okay. So d square v by dx square is equal to minus rho by e. And the second diagram that is related to the electric field, this can be written as electric field is equal to minus dv by dx. So that can be written as rho by epsilon, integral rho by epsilon into dx. So as you can see here, electric field intensity versus the distance along the device from the junction. And finally here, electrostatic potential equation I am writing here, V is equal to minus integral E into dx, sorry, E into dx. So as you can see here, a potential barrier is created. This is represented by its height. Height is represented in terms of voltage. Okay, V naught. So whenever a charge is created, finally we can see here a potential barrier is created with some height. Height is represented in terms of the voltage, in terms of volts, that is represented as V naught. So as you can see here, I can draw like this. This is minus and this is a plus, and this I am calling it as a V naught. So by the depletion region, finally we can see that a barrier potential with a height of V naught is created. So this barrier potential behaves like a wall which stops further movement of holes from p side to n side, and a similar diagram also can be drawn for the electrons. As you can see here, from n side to p side, no electron will be moved. Why? Because a wall is created. This can be represented as a potential barrier. So this V naught value depends on the type of material we use. Suppose we are using germanium material, the V naught value will be equal to 0.3 volts. Whenever you are using silicon material, V naught value will be equal to 0.7 volts. Okay. So at zero bias, a potential barrier is created inside the device with a potential of V naught volts. Okay, that is due to the formation of depletion region. Okay, which is represented as V naught. So this is a conclusion about zero bias. Zero bias, we are not going to apply any external voltage. Even though you are not applying any external voltage, by the diffusion mechanism, a depletion region will be created at the junction. By the depletion region, a charge is created here. A charge density is created by which the electric potential is created, and electric potential is represented as V naught. It is represented as a barrier potential, which is represented in terms of its height. Height is represented in terms of the volts, V naught. And V naught value will be 0.3 volts for germanium and 0.7 volts for silicon. So with this, I conclude this particular lecture. I will continue in the next class.